Good morning, my name is Artur Krasiński and I would like to present to you the results of our team's work on simulation of a sequential system using the S7-1200 platform and touch panel KTP700 in the context of technical education. In today's world, most control systems are based on PLC class controllers. Therefore, there is a great need to educate technicians and engineers in the field of designing programs, programming and simulation of such systems. The learning process should be supported by the ability to visually observe the results of own work. Of course, companies producing controllers and software tools for their programming provide the possibility of conducting simple simulation, but they are usually limited to observing the state of selected variables. However, it is difficult to observe the results of the implemented control algorithm only by interpreting a set of information about change in the state of certain variables. A much better solution is to observe the change in the physical state of the system being controlled, or if it does not exist, its virtual equivalent. There are software platforms that enable the certain and use of such virtual system, such as Factory I/O. However, they are relatively expensive and not all schools might be able to afford to implement such a solution. An alternative may be to use existing hardware resources in the form of HMI class operator panels, which, if working with a PLC controller, can to some extent replace more expensive solution for virtualization of control system. Figure shows the concept of such a system. It was composed of modern and popular elements in the industrial environment. Controller S7-1200 DC PLC, touch panel KTP700 basic, switch Scalance XB005, programming computer with TIA Portal V17 software. Let there be two simple examples to illustrate sequential behavior. Left figure shows an example in which the troller has to move sequentially to the right, to the position determined by the position of sensor X2, and to the left, to the position determined by the position of sensor X1. L move left and R move right. Signals were used of output signals enabling the correct direction of movement of the trolley. Each time the trolley reaches any end position X1 or X2, it should stop for 1 second. The sequence is to be repeated cyclically. Right figure show an example in which the trolley has to move according to a changed sequence. At the beginning of the sequence, the trolley should start moving to the right until it reaches the position determined by the position of sensor X3. Then it should move left until it reaches the position determined by the position of sensor X1. In the next step, it is to move to the right again, but this time up to the position determined by the position of sensor X2, while ignoring the signals from sensor X3. Then it should move left again until it reaches the position determined by the position of sensor X1. The sequence is to be repeated cyclically. Each time the trolley reaches any end position X1, X2 or X3, it should stop for 1 second. The illustration of the trolley's operating sequence are shown below. For such a specific problem, it was decided to prepare a framework of a software solution that would allow the trainees to observe the visual effect of their actions. The proposed solution is based on the use of two OB class blocks, called automatically by the controller operating system. The first block, called main, contains only a call to the FSM program block responsible for implementing the control algorithm, and the trainees should only focus on it. The second block, called simulation, contains K2 program blocks, inputs and line motion. The input blocks contains only simple program structure responsible for the proper preparation of input signal to the FSM block. The line motion block contains all structures used to generate responses by the virtual system. The internal program blocks were implemented as FB class function blocks. The logical connection of all blocks are present in this slide. The input signals to the FSM block are formatted in the inputs block based on information from the physical inputs. AG %A 0.0, %A 0.1, etc. and from the flags output of the line motion block. The flags signals was implemented as an 8-bit byte variable, depending on the solution adopted. It can be used to transmit information about the state of 8 bits flags or with full coding 256. The software structure forming the input signals to the FSM blocks can be implemented according to the diagram present in figure. Combining physical input signals with virtual signals allows to test the solution in various conditions, including real conditions after connecting to physical object. The structure of the line motion block is a little bit more complicated. The inputs to it are the output signal from the FSM block implementing the control algorithm. In addition, there is also a speed input, which can be used to configure the speed of moving the object trolley in the visualization, as well as an RST input used to reinitialize the block. The pause output gives information about the current position of the object, while the flag output contains information about reaching the set position determined by the position of sensor X1, X2, etc. Generating information about the state of virtual sensor may look as shown on the slide. If the value of the position variables is different from the declared value representing the position of specific sensor, the value 0 is entered into the flag variable. This means that none of the virtual sensor is active. If the position variable takes one of the value representing the position of the sensor, the code of the appropriate sensor will be entered into the flag variable. The declaration of values representing the position of all sensor was implemented in the line motion block interface as a set of constants with names position 1 to position 8. This makes it possible to work with 8 virtual sensors associated with a single object movement. Next slide shows an example of the visualization of a trolley object using the functionality of horizontal linear shifts. By shifting the position of sensor X1 and X2 50 and 550 relative to the initial and final position of the card on the simulation screen 0 and 600, it can be achieved the effect of forwarding the card beyond the sensor. This provides practitioners with insight into the consequence of their implementation of control sequence. For the second example with 3-position sensor, it is enough to modify the part responsible of generating information about the state of virtual sensors and change the value of the position 3 constant. The operation algorithms of both control systems can be presented using the popular behavioral description FSM model. And so in figure A there is presented a system with 2 sensors, and in figure B with 3 sensors. The sequence of action described in this way was carried out using the methodology widely presented in our previous works. It is based on the implementation of directed arcs connection individual states. For example, the arc connecting the S0 state with the S1 state can be realized as shown, where S0, S1 are internal binary variables assigned to individual states of the machine. In this fragment, it is checked whether the required state S0 is active and whether the condition for the machine to move to the next state is met. If so, the initial state S0 is deactivated, the final state S1 is activated, and the output signals are appropriately controlled. R signal reset. The system was presented this way and was put into practical implementation, and the system resources consumption was analyzed. The Siemens TIA portal and S7-1200 language was used for implementation as a very convenient PLC programming tool. In case of example 1, the implementation of the control algorithm itself includes the following blocks: mine 3969 bytes, FSM 7183 bytes, and FSM DB 1464 bytes. This gives a total of 12,660 bytes. The implementation of simulation block requires simulation 5,265 bytes, line motion 10,253 bytes, inputs 4,723 bytes, line motion dB 1,990 bytes, inputs dB 1464 bytes, which gives a total of 24,168 bytes, i.e. almost twice as much program memory, load memory. However, taking into account the slightly more complicated algorithm from example 2, it is clear that this difference is decreasing. Thus, the algorithm itself takes 50,993 bytes and the simulation 26,153 bytes. The described system was designed to play a role of cost-effective simulation solution to be applied in various educational situations. It was intended to be used in PLC programming, teaching, digital control system design, education, and so on, especially when there is limited access to resources such as physical models of devices, poor internet connection limiting use of simulation, or financial reasons not allowing to use licensed simulation solution. The system was implemented in practice and tested during classes related to programming PLC logic controllers. The system proved to be useful and it fulfills its task. On the other hand, use of such solution requires an increased amount of work from the teacher to prepare the PLC hardware and PC software, to load appropriate projects and configure them properly for conducting the exercises. The use of presented system causes increased load on the controller, especially in terms of the occupancy of its internal memory. The implementation of simulation introduces a large additional burden on the controller, but considering the significant available resources. This is an acceptable situation for small and medium-sized projects. It could be more problematic with development large projects, which is not very likely in educational situation. Thank you for your attention.